Hello everyone. I'm Fennel, and I'll be presenting our paper, The Perceptual Observatory, Characterizing Robustness and Grounding in MLLMs. Perceptual Observatory is a holistic framework that evaluates multimodal large language models through perception-first benchmarks and structure perturbations. So here we try to create a benchmarking framework and a pipeline, as well as insights in that reveal that are beyond the leaderboards that already exist. So we can see that with the recent growing of all of the large vision language models or large LLMs, you have Gemini, ChatGPT, Claude, Gwen, those are some of the frontier ones, and you have a couple of more open source as well. But what exactly is the uh, main problem with them? So what we noticed is that, for example, Gwen 2.5 VL, they have all of the 3 billion, 7 billion, and 72 billion parameter model have the same uh, vision transformer. So they only scale on the language side, although they have a vision language merger, which does scale, but exactly that's the fallacy because the vision language merger is something that does not completely align the vision and language side. If you keep on scaling the language side, you will still not be able to understand perceptually on what is actually going on. So, getting on to that, how you would test it. We created a dataset pipeline, which is exactly taking a ground truth. So in this scenario, we have two kinds of dataset. One is celeb and one is word. So on the celeb side, we have, let's say, Killian Murphy. We have 1,000 images. And we perturbed it with two different kinds. So one is something we call in distribution perturbation, and one is out of distribution perturbation. So in distribution perturbations are your pixel level augmentation like zoom, blur, Gaussian blur, chromatic aberration, etc. And your out of distribution perturbations are your illusion based. So I'll get on to it. This is some of the examples, although they might not look very different. If you were to look in a larger scale, you'll definitely see it. So how we created out of distribution perturbations. So here we have a pipeline. Let's say you have NLP. So looking at the NLP, it's a boxed white canvas and black text we have. You have a prompt. You have a diffusion model that is stable diffusion 1.5 as showcased. So we take in stable diffusion 1.5, we take the ground truth, and then we pass it on with the modified control net to get something of an illusion-based image such that it is blended in the text, the image that is created from the prompt. So here are different kinds of illusions that we created. So you can see Killian Murphy, for instance, but actually if you squint your eyes, you'll be able to see that it's Killian Murphy. But if it's on a large canvas, let's say a projector or a film size project, then you might not be able to recognize. You'll only see sands. So that is how the illusions are and why these illusions are important to be created in such a way because this have maintained their own attributes. So you can see the eyes are already exactly in the same place, the nose, the mouth, all the other attributes are same. It's just blended in the prompt that we have given. This is another example for Word. You can see WACV, how beautifully it is blended in the snowy mountains. Okay, so how do we assess them? We have this task of image matching. Image matching, here we take in one support image that is our ground truth, and we take in four options. Three of them belong to the same data set, and one of them is an out of distribution from another data set. So here, there is only one correct answer, which is the closest match, that is the support match is the option B. And option E and C are closely aligned embeddings that we take in. We have we change it, and we also take in different kinds of illusion. We take in different perturbations as well. So here we assess all different kinds of perturbations, and they have different ordering. So this is crucial as model will look at a longer context. It will take in 5 images. It will understand and it has to match the closest. Now these all images are 1024 plus 1024 in RGB. Now we move on to the actual. So humans perceive this abstract shapes. We are able to squint our eyes. We know what part of the image to look at, which and that is how we perceptually understand that what is actually going on in the image. But the models, they don't understand it this way. The models understand the image as a summary or a set of tokens, and they only look in a particular order from left to right, top down order. So models will definitely perceive them as semantics and they will fail. So moving on to the task 2, that is our grid pointing game. We basically align these 4 images into a grid with different orderings such that we have now created for one particular sample, we have now extrapolated to 4 different samples. And this also tests properties of models on how vision encoders are basically aligning, basically understanding the image part of it. So we can see that humans are invariant. You can change them into any order, keep them in any order. You can have a larger grid, and humans will still be able to recognize, oh, this looks like the closest match. But that is not so with the models. So the models perceive, and they have biases that will look further ahead. So the biases are such that the model will basically either look at the top left corner or the bottom right corner, and they are now susceptible to the locations as well. Coming to the third task. So task 3 is attribute localization. We do it in 2 scenarios. So one is what we call full guidance, and the other is we call partial guidance. Now, what is full guidance and partial guidance? Basically, can model fully localize all of the attributes if we give all of the attributes in the ground truth? And the partial guidance is basically we are only giving one particular attribute to the models, but now models have to identify all of the attributes for the given perturbation. Humans can perceive this, and humans are robust. They can easily be able to identify. Now, and this is why we created attributable perturbations in order to test whether they are just able to match it perfectly. Now, these are not only perturbations that we are taking, we are also taking in different samples, we are taking in ground truth as well. So giving the ground truth and its ground truth perturbations, are they able to recognize it for the ground truth image as well when nothing is changed? But models do not. Models are still sensitive. They give wrong bounding boxes and they don't actually localize. So coming to the main findings, we can see that even in throughout the task 1, 2, and 3, that is our image matching, grid pointing game, and attribute localization, we can see that the red marks basically showcase where there is a fallacy in the models. Here we test it with 3 different families. So one is Qwen 2.5, Gemma 3, and intern VL 3.5. Here, something to be noticed is that the intern VL 3.5 is also a reasoning model. It gives reasoning traces as well. So one of the conclusion that we can look at is that the stylized out of distribution perturbations, they basically are disproportionate and they harm the mid-scale models, even the larger models, and none of them are basically robust. So we can see that throughout all the tasks, there are more reds within the task, within the larger part, and the difference, the delta is greater. So there is a huge drop within the out of distribution perturbation. And robustness is not consistent. It doesn't improve with size. It's not guaranteed to improve robustness with size. We can see that Qwen 2.5 EL performs for the 3 billion performs better on word task 3 out of distribution than all of the rest. Now, why is that? One of the reason is, as we discussed earlier, that the vision encoder is held fixed, whereas the language side is being scaled. The language decoder is scaled by a huge margin. The second thing to notice is that even with thinking performance, for instance, for intern VL 3.58 billion and 14 million, with thinking on, it is still not able to identify. And humans do achieve more than 95% in almost all of the scenarios. So humans are invariant, they have the spatial understanding, and that is what we want. Going further, models should be made in such a way that are closer to that aligns with humans in a better sense. So some important findings that from grid pointing game, as I said earlier, that with the grid pointing game, we also assess whether the models are do they have positional bias? Are they invariant? What exactly is going on? So our insights reveal that the models have a gender bias and a positional bias as well. So we can see that for the in distribution, when 2.5, 72 billion is almost perfectly in the ideal zone, be it the skewed data set or not, it is able to recognize well for the in distribution images. Um, but it fails as we move to the out of distribution images. So the bigger models have a huge drop when you move from in distribution to out of distribution. We can also see that there is a drop. So if you look closely to the circular and the squared marks of the same model, the gap shows that the circular ones are the male and the squared ones are female. So there is a bias within the male, female, and position as well, which is not what an ideal model should be. Our task 3 also reveals that smaller models are more susceptible to the out of distribution, and it's quite evident that smaller models having vision tokens, but vision encoder, but they do not have the capabilities in order to understand it well on the language side. We can also see that average robustness to individual attribute performance reveal much higher gender bias. As I said earlier, in the task 3 also, it is revealed that there is a huge gender bias. We can see the gap of Qwen 3.5, Qwen 2.53 billion parameter model and Gemma 12 billion. So Gemma 12 billion has a smaller gap, whereas when 2.53 billion has a huge gap. So smaller models are more susceptible to the out of distribution and have a much larger gender bias. Some more interesting facts. So the thinking part. So as I said, intern VL 3.5 is also a reasoning. A reasoning model gives thinking traces, and we can see that the thinking tokens are not even if you increase the thinking length to, let's say, 3,000, 4,000 tokens. It is only thinking in the language side, it is not looking back. So that is one of the major fallacy, that the models are not thinking in back and forth way. So the problem is that even if you keep on increasing the thinking length, it will still not fix. The only part that they will fix will be at the start of the thinking trace. So any fixes will be at the start of the thinking trace. After that, it will not. And out of distribution will fail very easily. Some of the closing remarks, again, robustness is a bottleneck. There is a need for better, more strong data sets to assess the visual language models or multimodal language models holistically. Bigger model does not mean that you have better perceptual capabilities, as there is still non-monotonic uh, results in the robustness, and they may break under any distribution shift. We can also see that thinking is again conditional. It's not guaranteed that it will, any thinking trace will basically scale it further, or it will lead to better understanding of the images. So that is one of the key gaps, and models should produce better explanations. It should be perception first. it should answer, it should look back and forth. So future directions are taking this data set, training it to have a better perceptual capabilities for better post-training, property-based post-training methods. There is a need for more stylized out of distribution benchmarks and data sets. And we can design a language model in such a way that has a joint vision language scaling rather than scaling the vision and language separately. So you can see that the biggest model that I have seen so far is Pixtral 124 billion, which has 123 billion language decoder and 1 billion vision encoder. So why is there a huge gap? This is something that we need to look more closely. And you can go and try Perceptual Observatory yourself. It's a code and project link. And yep, thank you. If there are any questions,